Here's the funny thing. You're sitting there right now, made of atoms, carbon, oxygen, hydrogen, nitrogen, a little bit of phosphorus, some calcium. Now those atoms, they don't get old. A carbon atom in your body is the same carbon atom it was 4 billion years ago when it was cooked up inside some dying star. It doesn't wrinkle. It doesn't get tired. It doesn't forget where it put its keys. And yet you do. You're made of stuff that doesn't age, and somehow you age anyway. Isn't that strange? Isn't that the most peculiar thing you've ever heard? Because if the parts don't break down, why does the whole thing fall apart? By the time we're done here today, you're going to understand something very deep about this. You're going to understand that the reason your body falls apart, the reason everything falls apart, is not because of wear and tear in the ordinary sense. It's because of a law of physics, the second law of thermodynamics. And once you see what this law really means, you'll never look at yourself or your coffee or the entire universe quite the same way again. Let's start with something simple, something you do every morning, probably without thinking about it. You stir cream into your coffee. Now watch what happens. You pour in the cream, it makes a little white cloud, and then you stir round and round. And very quickly, the whole cup becomes a uniform tan color. The cream mixes with the coffee. Beautiful. Nothing special. But now I want you to think about something. Have you ever seen that process run backwards? Have you ever stirred your coffee and watched the cream unmix? Watched it gather itself back together into a little white blob while the rest of the cup turned dark again? No, you haven't. Nobody has. In the entire history of the universe, nobody has ever seen cream unmixed from coffee by stirring. Now, why is that? You might say, well, that's obvious. Things don't unmix. But that's not an explanation. That's just a restatement of what I asked. Why don't things unmix? Here's what's really strange about it. If you look at the motion of individual molecules, of atoms bouncing around in that coffee cup, all of those motions are perfectly reversible. If you took a movie of two atoms colliding, bouncing off each other, and you ran that movie backwards, it would look perfectly fine. It would look like a perfectly legal collision going the other way. Newton's laws don't care which direction time runs. At the level of atoms, there's no difference between the past and the future. And yet, when you put billions and billions and billions of atoms together, suddenly there's a huge difference between past and future. Cream mixes but doesn't unmix. Hot things cool down, but cool things don't spontaneously heat up. Eggs break but don't unbreak. Your body gets older but doesn't get younger. Where does this arrow of time come from? Where does this one-wayness come from when the fundamental laws are perfectly reversible? This is the question. This is what the second law of thermodynamics is really about, and it's the key to understanding why you age. You know, I used to show my students a trick. I'd take a movie of something simple, like a pendulum swinging back and forth, and I'd show it to them. Then I'd run it backwards, and I'd ask them, can you tell which way is forwards? They couldn't. A pendulum swinging looks exactly the same whether time runs forward or backward. It's perfectly symmetric. Then I'd show them a movie of a glass falling off a table and shattering on the floor. Run it forwards. It looks normal. Glass falls, hits the floor, breaks into 1,000 pieces. Run it backwards, and what do you see? 1,000 pieces of glass magically leap off the floor, assemble themselves into a perfect glass, and jump up onto the table. Everyone laughs. It looks absurd. It looks like a magic trick or a bad special effect. But here's what I want you to understand. There is nothing in the laws of physics that forbids that. Every single collision between every single piece of glass and every single air molecule, if you ran them all backwards, would be perfectly legal. The reversed movie is a possible physical process. But it never happens. Why? That's what we need to figure out. Let me give you another example. Suppose I have a box, and I put a divider down the middle. On the left side, I put some red gas. On the right side, I put some blue gas. Both at the same temperature, same pressure, everything nice and even. Now I pull out the divider. What happens? Well, you know what happens. The gases mix. After a while, you've got purple gas everywhere. Uniform, boring, mixed. Now here's my question. Each molecule of red gas is just bouncing around following Newton's laws. Each molecule of blue gas is doing the same thing. Every single collision is reversible. So why doesn't the purple gas ever spontaneously unmix back into red on one side and blue on the other? The answer is not that it can't happen. This is the important point. It's not impossible. There's no law of physics that forbids it. What happens is that it's just incredibly, fantastically, unimaginably unlikely. Let me show you what I mean. Suppose you have just 10 molecules. 5 red, 5 blue. You remove the divider. Now, at any given moment, each molecule could be on the left side or the right side. How many different arrangements are there? Well, each molecule can be in one of two places, so you have 2 times 2 times 2, 10 times. That's 2 to the 10th power. That's about 1,000 different arrangements. Out of those 1,000 arrangements, how many have all 5 red molecules on the left and all 5 blue molecules on the right? Just one. So if you wait around, eventually, by pure chance, you might see all the red molecules wander back to the left side. The probability is 1 in 1,000. Not great, but not impossible. You'd have to wait a while, but it could happen. But now let's make it more realistic. Let's say you have a mole of gas. That's about 6 times 10 to the 23rd molecules. An enormous number, Avogadro's number. Now how many arrangements are there? It's 2 to the power of 6 times 10 to the 23rd. That's a number so big I can't even begin to describe it to you. It's bigger than the number of atoms in the observable universe. It's bigger than any number you've ever thought about. And out of all those arrangements, only a tiny, tiny, tiny fraction have all the red molecules on one side and all the blue molecules on the other. The probability of the gas spontaneously unmixing is so small that you could wait for the entire age of the universe 1 trillion times over and you'd never see it happen. Not once. So it's not that unmixing is forbidden. It's that it's so improbable that for all practical purposes it never happens. And that's what the second law of thermodynamics is really saying. It's not a fundamental law in the same way that Newton's laws are fundamental. It's a statistical law. It says that things tend to go from less probable arrangements to more probable arrangements, simply because there are so many more probable arrangements. Now, we need a word for this. We need a way to measure how many arrangements a system has. And that word is entropy. Entropy is, roughly speaking, a measure of disorder. But I want to be careful here because disorder is a tricky word. What entropy really measures is the number of different ways you can arrange the microscopic parts of a system while the system still looks the same from the outside. Let me give you a very simple analogy. Suppose you have a deck of cards, 52 cards. And I tell you, I want you to arrange this deck so that all the spades are together, then all the hearts, then all the diamonds, then all the clubs, and within each suit, the cards are in order from ace to king. How many ways can you do that? Exactly one way. There's only one arrangement that satisfies all those conditions. But now, I say, shuffle the deck. Make it random. How many arrangements count as random? Well, there are 52 factorial different arrangements of a deck of cards. That's about 8 times 10 to the 67th. An enormous number. A truly mind-boggling number. So if you start with a sorted deck and you shuffle it, you're almost certainly going to end up with some random-looking arrangement, because there are so vastly many more random arrangements than sorted ones. And if you start with a random deck and you keep shuffling, you're never going to end up with a sorted deck, because the probability is about 1 inch 10 to the 67th. You'd have to shuffle more times than there are atoms in the universe. That's entropy. The sorted deck has low entropy. Very few arrangements look sorted. The shuffled deck has high entropy. Almost all arrangements look shuffled. And the second law says entropy tends to increase. Not because there's some mysterious force pushing things toward disorder, but simply because there are so many more high entropy states than low entropy states that you're almost certain to end up in one. Now let me push this analogy a little further, because I think it's really helpful. Suppose you're a card counter, like those fellows in the casinos. You're very good at keeping track of cards. You know exactly which cards have been played. In other words, you have information about the state of the deck. When the deck is sorted, it's easy to describe. You can tell someone the complete state of the deck in just a few words. It's in perfect order. That's it. Very low information content, in a sense. But when the deck is shuffled, to describe its exact state, you'd have to list all 52 cards in sequence. That takes much more information. The shuffled deck has high entropy precisely because it would take a lot of information to specify exactly which one of the gazillions of possible shuffled arrangements it happens to be in. This is actually a deep connection. Entropy and information are related. Low entropy means the state is easy to describe, predictable, ordered. High entropy means the state is hard to describe, random, disordered, and when information is lost, entropy goes up. When you shuffle the deck, you're losing information about its state. Before shuffling, you knew exactly where every card was. After shuffling, you don't. That loss of information is intimately connected to the increase in entropy. This is going to matter a lot when we talk about aging, because aging is, in a very real sense, a loss of information. The information about where everything should be in your body gets degraded over time. The patterns get blurrier. The organization gets harder to maintain. But I'm getting ahead of myself. Let me come back to the main question. Now, here comes the big question. What does any of this have to do with you getting old? Well, let me ask you something. What are you, exactly? From a physics point of view, what is a human being? You're a very complicated arrangement of atoms, about 7 times 10 to the 27th atoms, actually. 7 billion atoms. And these atoms are not arranged randomly. They're arranged in incredibly specific patterns. You've got proteins folded into precise three-dimensional shapes. You've got DNA wound up in chromosomes with billions of base pairs in exactly the right order. You've got membranes and organelles and cells all organized into tissues and organs. You are a low-entropy system. You are like a sorted deck of cards. You are one of the very, very few arrangements of atoms that happens to be alive. And the second law is constantly, relentlessly pushing you toward higher entropy, toward disorder, toward being more like a shuffled deck. Now wait, you might say. Wait a minute, Feynman. If entropy always increases, how did I get organized in the first place? How did this low entropy arrangement of atoms come to exist at all? Ah, that's a wonderful question. And the answer is, you're not a closed system. See, the second law says that entropy increases in isolated systems. Systems that don't exchange energy or matter with their surroundings. But you're not isolated. You eat food, you breathe air, you radiate heat. You're constantly exchanging matter and energy with the rest of the universe. And here's the trick. Here's how life works. You take in low entropy stuff from your environment, highly organized molecules like sugars and proteins and fats, and you use the free energy in that stuff to maintain your own organization. And then you export high entropy stuff back out. Heat, carbon dioxide, other waste products. So your entropy doesn't have to go up as long as you're increasing the entropy of your surroundings by at least as much. You're like a refrigerator. A refrigerator can make the inside cold, can decrease the entropy inside, but only by dumping even more heat out the back, increasing the entropy of the room. The total entropy of refrigerator plus room still goes up. The refrigerator just moves entropy from one place to another. You do the same thing. You maintain your low entropy state by exporting entropy to your environment. You eat order and excrete disorder. That's what metabolism is, fundamentally. That's what being alive means, from a physics point of view. Let me give you a concrete example of what I mean. Think about what happens when you eat an apple. The apple is a highly organized structure. Sugars, fibers, vitamins, all arranged in specific molecular patterns. Low entropy, at least compared to the final products. You eat the apple, your digestive system breaks down those complex molecules into simpler ones. Glucose, amino acids, fatty acids. This releases energy, which your cells capture in the form of ATP, the energy currency of life. Now you use that ATP to do work, to build proteins, to repair DNA, to contract muscles, to fire neurons. All of this requires energy. And all of this requires maintaining specific molecular arrangements against the constant thermal jiggling of your environment. And what happens to the waste? The glucose you've broken down combines with oxygen and becomes carbon dioxide and water. The carbon dioxide you breathe out, the water you excrete. These are simpler molecules than what you started with. Higher entropy. So the total picture looks like this. Apple plus oxygen goes in, low entropy. Carbon dioxide plus water plus heat goes out, high entropy. And in the middle, you maintain your organization for one more day. You're a machine that converts low entropy food into high entropy waste and uses the energy difference to keep yourself ordered. Beautiful, really. Absolutely beautiful. Schrödinger, the great quantum physicist, put it wonderfully. He said that what an organism feeds upon is negative entropy. Or, to put it less paradoxically, what life does is extract order from its environment. We drink orderliness from the world around us. But here's the catch. Here's why you still age. You can fight entropy for a while. You can maintain your organization, keep your proteins folded, repair your DNA, replace worn-out cells, but you can't fight it forever. And here's why. Every time you do anything, every time you repair some damage, every time you maintain some structure, you use up free energy. You degrade some high-quality, low-entropy energy into high-entropy waste heat. And there are losses. There are always losses. Your repair mechanisms themselves are made of molecules. And those molecules get damaged too. And the molecules that repair those molecules also get damaged. It's repair all the way down, and at every level there are errors. There are mistakes. The repair is never perfect. Think of it like making copies of copies. If you photocopy a page, it looks pretty good. Photocopy the copy, still okay. But photocopy the copy of the copy of the copy 100 times, 1,000 times, and eventually you can't read it anymore. The errors accumulate. That's what's happening in your body at the molecular level all the time. Your DNA gets hit by radiation, by free radicals, by random thermal fluctuations. Your repair enzymes fix most of the damage, but not all of it. And the repair enzymes themselves are encoded by DNA that's getting damaged. It's a slow, relentless accumulation of errors. Let me put some numbers on this so you can appreciate the scale of what we're talking about. Every single day, in every single cell of your body, your DNA gets damaged tens of thousands of times. Tens of thousands of lesions, broken bonds, crosslinks, oxidative damage. It's constant. It's relentless. And every single day, your repair machinery fixes almost all of it. We have dozens of different repair pathways. Base excision repair, nucleotide excision repair, mismatch repair, double-strand break repair. Your cells are constantly proofreading and fixing and patching. But here's the thing. Not all the damage gets fixed. Some of it slips through. Maybe 1 in a billion errors survives the repair process on any given day. Sounds like a small number, right? But you have trillions of cells, and they live for decades. 1 in a billion times a trillion cells times decades of days, and you're talking about billions of accumulated errors, and those errors compound. An error in a repair enzyme makes that enzyme less effective, which means more errors get through, which means more damage to other repair enzymes, which means even more errors get through. It's a vicious cycle. This is what gerontologists call the disposable soma theory. The idea is that evolution didn't optimize you for immortality, evolution optimized you for reproduction. And from evolution's point of view, it's more efficient to build a body that works well for a few decades, long enough to reproduce and raise offspring, and then falls apart, rather than to build a body that works forever but requires much more resources to maintain. Think about it. If you wanted to build a car that lasted 1,000,000 years, you could do it. You'd use better materials, add more redundancy, include more maintenance systems, but it would be incredibly expensive. It's much more economical to build a car that lasts 20 years, because that's long enough for most purposes. Your body is the same. Evolution found the economical solution, good enough for reproduction, and then who cares? From the gene's point of view, you're just a temporary vehicle anyway. Harsh? Maybe, but that's the logic of natural selection, and it meshes perfectly with the physics of entropy. And there's another thing. Even if your repair mechanisms were perfect, which they're not, they would still require energy. And getting that energy produces entropy, produces heat, produces waste. You can't run the machinery of repair without generating disorder somewhere. So here's the deep truth. The reason you age is not because your parts wear out exactly. Your atoms don't wear out. The reason you age is that maintaining order, fighting entropy, is a losing battle in the long run. You can win the battle for a while. You can stay organized, stay alive for decades. But eventually, the errors accumulate. The repair mechanisms falter. The organization breaks down, and entropy wins. You return to equilibrium. Your atoms get recycled back into the environment to be used by other organisms, other life forms, fighting their own temporary battles against the same inexorable law. Now, I want to be careful here. I want to make sure you really understand this, because there's a common misconception I need to address. Some people hear about entropy in the second law and they say, aha, so evolution is impossible. How can complex life evolve if entropy always increases? How can you get more order over time? But this is a misunderstanding. This confuses local entropy with global entropy. Let me explain this with an example. Suppose you have a pot of water on a stove. You turn on the heat, what happens? The water starts to circulate. It forms convection cells. Hot water rises in the middle, cools at the edges, sinks down, gets heated again, rises. You get these beautiful, organized patterns of circulation. Now, wait a minute. I just said entropy tends toward disorder. But here we have order emerging spontaneously. The water is organizing itself into patterns. What's going on? The answer is that you have to look at the whole system. Yes, the water is becoming more ordered, but the stove is burning fuel, generating lots of heat, increasing entropy somewhere else, and the water is radiating heat into the room, increasing entropy even more. The total entropy of stove plus water plus room is definitely increasing. The water can become locally ordered because it's exporting entropy faster than it's creating order. This is a general principle. Whenever you see order emerging spontaneously, look for the entropy export. Look for where the disorder is being dumped. A hurricane is a highly organized structure. It's not random. It has spiral arms and an eye and defined wind patterns. Where does that organization come from? From the heat of the tropical ocean, which the hurricane dissipates into the upper atmosphere. The hurricane is a machine for moving entropy from the warm ocean to the cold sky, and its beautiful spiral structure is a byproduct of that process. A snowflake is an exquisitely ordered crystal. Six-fold symmetry, intricate patterns, no two alike. Where does that order come from? From the release of latent heat when water vapor freezes. That heat gets dumped into the surrounding air, increasing its entropy. The snowflake's organization is paid for by the disorder it creates in its environment. Evolution doesn't violate the second law. Evolution is powered by the sun. The sun is a gigantic source of low entropy energy. It takes hydrogen atoms and fuses them into helium, releasing vast amounts of high-quality electromagnetic radiation. That radiation hits the Earth. Plants capture it and use it to build organized molecules out of carbon dioxide and water. Animals eat the plants. The whole biosphere is a giant engine driven by the steady flow of low-entropy energy from the sun, exporting entropy out into space as waste heat. So life on Earth can become more complex, more organized, more ordered, because we're not an isolated system. We're connected to the sun. We're surfing on a river of negative entropy, as Schrödinger might say. Life doesn't fight the second law. Life uses the second law. Life is what happens when a system finds a way to channel the universal tendency toward disorder through complex, self-replicating patterns. We're not exceptions to the rules of physics. We're consequences of them. But here's the thing. Even the sun is running down. The sun is converting its nuclear fuel into energy, and eventually it will run out. In about 5 billion years, the sun will exhaust its hydrogen, swell into a red giant, and then collapse into a white dwarf. The free energy will be gone, and on an even larger scale, the whole universe is running down. All the stars are burning their fuel, radiating energy into the void, and eventually, in the very, very far future, all the useful energy will be gone. The universe will reach maximum entropy. Every place will be the same temperature. Nothing will be able to happen. This is sometimes called the heat death of the universe. Now, let me be clear about what I mean by nothing will happen. I don't mean the universe will be empty. There will still be particles, still be space. But there won't be any temperature differences, no gradients, no flows, no possibility of doing work. Think about a waterfall. The water at the top has potential energy. It can do work as it falls, turn a mill wheel, generate electricity. But once it's at the bottom in the calm pool, it can't do any more work. It's at equilibrium. The heat death is like the whole universe being at the bottom of the waterfall. All the energy is still there, but it's all spread out evenly. There's nothing for it to flow toward, nothing for it to do. This is a strange and melancholy thought. Trillions of years from now, when the last stars have burned out and the last black holes have evaporated and everything has reached the same temperature, the universe will be dead. Not dark, exactly, just boring, nothing happening, nothing able to happen, maximum entropy, perfect disorder, the end. But here's what I want you to take away from that. We live in a special time, a brief window. The universe started in a very low entropy state for reasons we don't entirely understand, and it's been increasing ever since. And during this increase, during this flow from order to disorder, complex things can happen. Structures can form, life can arise, you and I can exist. We're like eddies in a river. The river flows from the mountains to the sea, from low entropy to high, and we're little whirlpools that form along the way. Temporary, brief, but real, and beautiful. So, in the longest run, entropy wins. Entropy always wins. But that's not a reason to despair. It's just the way things are. And in the meantime, in the brief cosmic moment that we call life, we get to exist. We get to be these temporary, improbable, beautiful arrangements of matter that can think about ourselves and wonder why we're here. Let me give you a thought experiment, a way to really feel what entropy means for aging. But first, let me tell you about a famous puzzle that kept physicists scratching their heads for almost a century. It's called Maxwell's demon. James Clerk Maxwell, who figured out the laws of electromagnetism, proposed this thought experiment. Imagine you have a box full of gas at some temperature. The molecules are bouncing around, some fast, some slow. The temperature is just the average speed. Now imagine there's a little demon, a tiny intelligent being, sitting in the middle of the box with a trap door. When he sees a fast molecule coming from the left, he opens the trap door and lets it through to the right. When he sees a slow molecule coming from the right, he lets it through to the left. He doesn't have to push the molecules or exert any force. He just opens and closes the door at the right moments. What happens? After a while, all the fast molecules are on the right side, and all the slow molecules are on the left side. The right side is now hot, and the left side is cold. You've separated hot from cold without doing any work. But that's impossible, according to the second law. You can't decrease entropy without doing work. Heat doesn't flow from cold to hot spontaneously. What's going on? This puzzle bugged physicists for decades. The answer, which wasn't fully worked out until the 20th century, is subtle and beautiful. The demon has to observe the molecules. He has to get information about them, and getting information requires physical processes that generate entropy. Every time the demon looks at a molecule and decides whether it's fast or slow, he has to store that information somewhere, in his brain or in some kind of memory. And when he erases that information to make room for the next observation, the erasure generates entropy. There's a fundamental connection between information and thermodynamics. Erasing one bit of information generates at least k log 2 of entropy. That's about 10 to the minus 23 joules per Kelvin. Tiny, but not zero. So the demon can't cheat. The entropy he creates by processing information is at least as much as the entropy he reduces by sorting molecules. The total entropy still goes up. The second law wins. Now, why am I telling you this? Because it connects to what I said earlier about information and aging. Your body is like Maxwell's demon. It's constantly observing and sorting. Your enzymes recognize specific molecules and catalyze specific reactions. Your immune system identifies foreign invaders and destroys them. Your DNA repair machinery detects damage and fixes it. All of this requires information processing. And information processing generates entropy. Your body is swimming against the entropic current, using information to maintain order, but every time it processes information, it generates more disorder downstream. This is a deep way to understand aging. Aging is, in part, the accumulation of information loss. The patterns get noisier, the signal gets degraded, the sorting gets less precise. Eventually, the noise overwhelms the signal, and the organization falls apart. Now let me give you another way to see this. Imagine you have a jigsaw puzzle, 1,000 pieces. You've put it together perfectly, and it shows a beautiful picture. Maybe a landscape, mountains, and a lake. Now I'm going to shake the table gently, once a day, every day, one shake. After the first shake, the puzzle is probably still intact. Maybe one piece got jostled slightly out of position. You can fix it easily, push it back in. After 100 shakes, several pieces are out of place. You spend a few minutes putting them back. Still doable. After 1,000 shakes, some pieces have moved so far they're in the wrong parts of the puzzle. You spend an hour putting everything back. You notice that a few pieces are getting worn, their edges fraying a bit. Your repairs are not quite as good as the original. After 10,000 shakes, large sections of the puzzle are scrambled. You spend all day fixing it. Some pieces are so worn they don't fit properly anymore. The picture is getting fuzzy. After 100,000 shakes, you're spending more time repairing than doing anything else. The puzzle is more patched than original. Large parts don't fit together at all anymore. The picture is barely recognizable. Eventually, inevitably, there comes a shake that you can't recover from. The puzzle is destroyed. The beautiful picture is gone. All you have is a box of disconnected, worn-out pieces. That's aging. That's what's happening to you right now, at the molecular level. The shakes are thermal fluctuations, radiation hits, chemical accidents. The repairs are your DNA repair enzymes, your immune system, your cellular maintenance machinery. And the wearing out of the pieces, that's the accumulation of damage that your repair systems can't quite fix. Now let me tell you something wonderful about all this, something that I find deeply moving. We often think of physics as cold, abstract, far removed from human concerns. But here we are, at the very heart of physics, at the deepest laws of nature, and what do we find? We find an explanation for mortality. We find a reason why all things must pass. The second law of thermodynamics is not just about heat engines and gas molecules. It's about time itself. It's about the arrow of time, why the past is different from the future, why we can remember yesterday but not tomorrow. It's about change and decay and the impermanence of all things. And it's about life, too, because life is a process. Life is a way of borrowing order from the universe, temporarily, maintaining a pocket of low entropy in a sea of increasing disorder. Life is a flame, burning bright for a while, fed by the fuel of free energy, and eventually guttering out. But what a flame, what a magnificent, improbable, beautiful thing to be. You know, when you understand entropy, you understand why every moment is precious, because every moment is borrowed. Every second of your life, you are fighting a battle against the fundamental tendency of the universe toward disorder. And for a few decades, incredibly, you win. You maintain your organization. You stay alive. You think. You feel. You love. You wonder. And then, eventually, entropy catches up with everyone. That's not a tragedy. That's just physics. That's just the way the universe works. I want to talk a little bit about the mathematics now. Just a little. Because I promised I would. And because it's actually quite beautiful once you see it. The key equation is Boltzmann's formula for entropy. It goes like this. S equals K log W. S is the entropy. K is Boltzmann's constant, a tiny number that connects the microscopic world to the macroscopic world. And W, this is the important part, W is the number of microstates. What's a microstate? It's a complete specification of what every particle in the system is doing. Its position, its velocity, everything. A macrostate is what you can measure from the outside. Temperature, pressure, volume, that sort of thing. Here's the point. Many different microstates can correspond to the same macrostate. When I say the gas is at a certain temperature and pressure, there are gazillions of different arrangements of molecules that would give that same temperature and pressure. W is the number of those arrangements. And entropy is just the logarithm of W. If there are more ways to arrange the microscopic parts while keeping the macroscopic properties the same, the entropy is higher. Now, why the logarithm? That's a very good question. Let me tell you why. Suppose you have a system with W, one possible arrangements, and another independent system with W, two possible arrangements. How many total arrangements are there for the combined system? It's W1 times W2, because for each arrangement of the first system, you can have any arrangement of the second. But entropy should be additive. If I have 2 cups of coffee, the total entropy should be twice the entropy of 1 cup. Entropy of the whole equals entropy of the parts added together. And here's the beautiful thing about logarithms. Log of a product is the sum of the logs. So log of W1 times W2 equals log W1 plus log W2. The logarithm automatically gives you additivity. S total equals S1 plus S2. Very convenient. Boltzmann knew what he was doing. So when I say high entropy states are more probable, this is what I mean. They correspond to more microstates. There are more ways to be disordered than to be ordered, that's all. Boltzmann was so proud of this formula that he had it engraved on his tombstone. S equals K log W. It's one of the most profound equations in all of physics. It connects the microscopic world of atoms and molecules to the macroscopic world of heat and temperature and irreversibility. It explains why time has a direction. It explains why your coffee cools and your body ages. And it does all of this just by counting, by asking how many ways there are to arrange things. That's it. No mysterious forces, no exotic physics, just counting and probability. That's the genius of statistical mechanics. It reduces the deepest questions about time and change and mortality to arithmetic. Now, living systems. What's special about living systems thermodynamically? Living systems are what we call dissipative structures. They exist far from equilibrium. They maintain their organization by continuously dissipating energy, by continuously producing entropy and exporting it to their surroundings. A candle flame is a dissipative structure too. It's organized in its way. It has a shape, a structure. But it only exists as long as there's fuel and oxygen. Cut off the fuel, and the flame goes out. The organization disappears. You're the same way, just much more complicated. You only exist as long as there's food and air and water. Cut off the supplies, and you stop. The organization breaks down. Your atoms disperse back into the environment. The difference between you and a candle is complexity. The flame has a simple organization that can be maintained by a simple chemical reaction. You have an incredibly complex organization that requires incredibly complex machinery to maintain DNA replication, protein synthesis, cell division, immune response, neural signaling. Thousands of different processes, all working together, all requiring energy, all producing entropy. And here's the catch. The more complex the organization, the more ways there are for things to go wrong, the more damage that can accumulate, the more vulnerable you are to the creeping disorder of entropy. A crystal is very simple. It can maintain its structure for billions of years because there's not much to go wrong. The atoms are locked in place by strong bonds. Entropy has to work very hard to disrupt a crystal. But you're not a crystal. You're a dynamic, far from equilibrium, fantastically complicated system. Your proteins are not locked in place. They're jiggling and folding and unfolding and interacting. Your cells are dividing and dying and being replaced. Your DNA is being copied and repaired and sometimes mutated. There are so many more ways for you to be disordered than to be properly ordered. That's why entropy catches up with complex organisms faster than with simple things. That's why you age in decades while rocks last for eons. Here's another way to think about it. Your genome, your DNA, contains about 3 billion base pairs. That's the instruction set for building and maintaining you. It's an incredibly long message written in a 4-letter alphabet. Now, how much entropy does that represent? How much information? If each base pair can be one of 4 possibilities, and you have 3 billion of them, then the number of possible genomes is 4 raised to the power of 3 billion. That's an unimaginably large number. It's larger than the number of atoms in the observable universe, raised to the power of the number of atoms in the observable universe. But out of all those possible genomes, only a tiny fraction correspond to anything that would actually work. Most random sequences of base pairs would produce nothing viable. You need very specific sequences to get a living organism. So your genome is a needle in a haystack, an incredibly improbable arrangement, low entropy, and maintaining that arrangement, copying it accurately when cells divide, repairing it when it gets damaged. That's the fundamental challenge of life. That's what your body is doing constantly just to keep you alive. And here's the terrible truth. The longer you do this, the harder it gets. The copies get noisier, the repairs get less precise, the needle slowly dissolves back into the haystack. Now let me say something else. Something about the beauty of all this. You might think, hearing all this, that the universe is against us, that entropy is the enemy, that physics is conspiring to destroy everything we love. But that's not the right way to see it. Entropy is not your enemy. Entropy is what makes life possible in the first place. Think about it. If everything were already at maximum entropy, if everything were at equilibrium, nothing would ever happen. There would be no gradients, no flows, no changes. The universe would be dead, boring, unchanging. It's precisely because the universe started in a low entropy state, because there were gradients and differences and potential, that anything interesting could happen at all. The arrow of time, the flow of events from past to future, the whole history of the cosmos, it all comes from that initial low entropy. And life rides that arrow. Life exploits those gradients. Life captures free energy and uses it to build complexity and organization. Without entropy, without the second law, without that constant flow from order to disorder, there would be no life. There would be no us. So entropy is not the enemy. Entropy is the current we swim in, the river that carries us. We exist because of entropy, not despite it. And yes, eventually the river reaches the sea. Eventually entropy catches up with all of us. But the journey, the brief, improbable, magnificent journey, that's what matters. That's what's real. That's what we have. I want to close with a few more thoughts. People often ask me, Feynman, what's the point? If everything falls apart, if entropy wins in the end, what's the point of anything? And I always say the same thing. The point is not the destination. The point is not some final state that lasts forever. The point is right now. The point is the journey. The point is being here, being alive, being aware, being able to understand even a little bit of how the universe works. You know, there's a tendency in human thinking to want things to be permanent, to want meaning to be tied to permanence. If it doesn't last forever, it can't really matter, right? But I think that's exactly backwards. Consider a flower. It blooms, it's beautiful for a few days, and then it wilts. Does that make it meaningless? Should we not bother with flowers because they don't last? Of course not. The flower is beautiful precisely during its brief existence. Its impermanence is part of what makes it precious. You notice it, you appreciate it, because you know it won't be there forever. Or think about music. A symphony is played, the notes sound, and then they're gone. The air returns to stillness. Did the symphony not matter because it didn't last? Of course it mattered. The experience was real. The beauty was real. The fact that it ended doesn't erase the fact that it happened. I think the same is true of life, of consciousness, of you. You are made of atoms that were forged in stars. You are arranged in patterns that took 4 billion years of evolution to develop. You can think about yourself, wonder about your own existence, contemplate the laws of physics, that govern your own mortality. That's astonishing. That's miraculous. That's the most amazing thing in the entire universe. And yes, it doesn't last forever. Nothing does. But so what? Does a sunset have to last forever to be beautiful? Does a piece of music have to play eternally to be moving? Does love have to be immortal to be real? The impermanence is not a flaw. The impermanence is part of what makes it precious. If you could live forever, would you appreciate any particular moment? If nothing ever changed, would anything ever matter? You know, I sometimes imagine what it would be like to live in a universe at maximum entropy. Everything, the same temperature, nothing happening, perfect equilibrium. It sounds terrible. It sounds like death, which in a sense it is. No change means no life. No gradient means no possibility. Complete order, if you like, or complete disorder, depending on how you look at it. But either way, complete stasis, complete boredom. We live in the interesting universe, the universe where things happen, where gradients exist, where energy flows, where complex structures can form and persist for a while before dissolving back into chaos. And that, for a while, is everything. That's the whole story. The universe starts ordered, ends disordered, and in between, there's us, there's life. There's consciousness. There's love and music and science and all the things that make existence worthwhile. Entropy is not your enemy. Entropy is your teacher. It teaches you that time is real, that moments are finite, that everything you have and everyone you love exists only for a little while and therefore is infinitely valuable. So don't fight entropy. Don't resent it. Understand it. Appreciate it. And then go out and live your brief, beautiful, low entropy life as fully as you possibly can. That's physics. That's thermodynamics. That's the universe. And that's why your body falls apart. Not because the atoms wear out, but because the dice keep rolling, the arrangements keep shuffling, and entropy, patient and inexorable, claims everything in the end. But not yet. Not today. Today, you're still here. Still fighting the good fight. Still maintaining your improbable organization against the overwhelming tide of disorder. So go use that organization while you have it. Go think. Go feel. Go wonder. Go live. That's the only answer physics has to offer. And I think it's a pretty good one. Now, I'm curious. Having heard all this, what do you think? Does understanding the physics of aging change how you feel about mortality? Or does it just make you want a cup of coffee? Write and tell me what you think.